Hi everyone, my name is Marcy Cruz, and today I'm going to be giving a short presentation on knot theory, specifically the knot invariant, the Jones polynomial. To begin, we're going to start with a short introduction to knots, including a definition, followed by a discussion of the Reidemeister moves and their relation to knot equivalence, after which we will define a knot invariant, and finally, which will allow us to move into our discussion on the Jones polynomial. So to begin, what exactly is a knot? I'm sure most of us use knots nearly every day, at the very least to tie our shoes. But there's one critical distinction between the standard knots we know in our day-to-day lives and a mathematical knot. And that's that a knot in the mathematical sense is a closed loop. It's an embedding of a circle in three-dimensional Euclidean space. Here we have a few different examples of knots. The most trivial being the unknot, but we also have the truffle and the figure eight, which we'll examine further in the slides to come. Um, as you can probably imagine by now, we are talking about a one-dimensional object in three-dimensional space and representing that on the two-dimensional plane. So we have to be a little careful with how we represent such an object. Um, what we use is called a knot diagram, which is a projection of the knot onto R2, where we represent any crossings as a break in the segment. Um, and this correlates to a segment passing under another segment. We can also choose an ordering to these crossings, and when we do so, we refer to this as the directed knot diagram, two examples of which we have here, which are the left and right-handed trefoils. Um, so the first question that comes to mind when seeing these diagrams is probably, are these the same? And from that, how do we tell two different knots apart? We will return to this question on whether or not the two trefoils are the same or different knots. But just to consider it, like they have the same shape, they have the same number of crossings. The only thing that differs is the relation of these crossings, the over-under relation of each strand. Um, so to return to a question on how do we distinguish knots, this is the hard question of knot theory. Right now, there is no universal tool that applies to all knots that can always that can always key us into when two knots are different. Um, and it really is a difficult question. For simple knots, it's easy enough to just brute force it and check. As with this example here, we have the unknot, and we have two representations of the unknot. They look very different. A circle versus this kind of twisted up curve. But if you really examine it, it doesn't take much to just kind of unfold this curve, which we can do. We can manipulate the knot in any way that doesn't break the strand, that doesn't um, pass two strands through each other, and that doesn't take a loop and squeeze it out into a point. Um, and what this boils down to is three moves that we refer to as the Reidemeister moves. So what we can do is we can take a strand and we can introduce or remove a loop. We can take two strands and slide them across each other, or we can take a strand and move it across some crossing. And again, as long as we're cutting the knot or passing a strand through another strand, we're good to go. And this leads us into Reidemeister's theorem, which essentially states that two knots are equivalent if and only if we can transform one knot into another through a finite application of Reidemeister moves. Um, we have an example of this process here using the figure eight knot. As you can see, after a finite number of moves, we have transformed the figure eight knot into its mirror image. This lets us definitively say that these two knots, well, I guess it's the same knot, but the figure eight knot and its mirror image are equivalent knots. This isn't true of all knots. And um, how we examine this is through the use of knot invariants. And what these are properties or quantities that we assign to a knot that remain unchanged regardless of how we deform that knot. Um, in particular, we will be examining a polynomial invariant, the Jones polynomial. And before we get to this, we must first define one more property, which is called the Reith of a knot. And what this is basically the sum of its crossings. And we assign a value to each crossing in accordance to the right-hand rule. So as on the left, that would be a positive crossing, whereas the crossing on the right would be a negative crossing. This isn't an invariant in itself, but it is necessary for us to compute the Jones polynomial. And it's clearly not invariant because you can take any diagram and using a Reidemeister one move, we can introduce new crossings. So that will either increase or decrease its Reith. So it can't be um, if the Reiter-Meister moves result in the same knot, then we can't have the Reich be an invariant since we can apply this move and have the same have the same knot but a new diagram with a new Reich. Anyways, to define the Jones polynomial, we have this following relation. So to begin, the Jones polynomial is a Laurent polynomial, which means it has both negative and positive exponents. And we define it recursively as follows. The Jones polynomial of the unknot is equal to 1. And beyond that, we have a what we call a skein relation, which allows us to take some crossing and decompose it into two simpler crossings. And the goal is to take the crossings of a knot diagram and decompose it into a collection of unknots. In doing this process, we construct this equation. And what this does is reduces our problem of distinguishing these knots into an algebraic one. I don't have the uh, I plan to add an example of this being worked out, but as of now, I'm just going to show a couple of examples of these polynomials. The first being the figure eight knot. As we have shown priorly, the figure eight knot is equivalent to its mirror image. This um, is shown in its Jones polynomial through this palindromic structure. The exponents of each variable are um, it has a corresponding negative exponent. So we can take the exponents, multiply them by -1, and it will not change the polynomial. However, this is not true when it comes to the trefoil, which, as we can see, um, has the same structure, but the exponents are negatives. They're inverses of each other. And this is the beauty of the Jones polynomial. It allows us to identify what we call chirality. When two knots are when a knot is not equivalent to its mirror image, then we say that is a chiral knot. However, with the figure eight knot, that would be what we call an achiral knot, which basically means it is equivalent to its mirror image.